that the periodic table can help us figure out, how many bonds an element is likely to form. Right? And what we're going to do is we're going to draw Lewis structures to show sort of where the electrons are in the context of molecules, okay, as opposed to in the context of atoms. So we did orbital filling for thinking of individual atoms, and now we're going to pretty much ignore all the core electrons and just worry about the valence electrons as we talk about forming molecular compounds, covalent compounds. But what's important to know is that some electrons will be involved in bonding, and some electrons will not be part of a bond. They'll still be there, okay, but we'll call them lone pairs, right? So here we have, a molecule formed between hydrogen and fluorine, so hydrogen fluoride. Okay, if you watched Breaking Bad, you will have, encountered this molecule as the one they used to dissolve a body in the bathtub, and it dissolved the bathtub and fell, through the floor. It's the only scene of Breaking Bad I've ever seen, because somebody asked me about it in the context of HF. But this molecule is also one that is used. So all of you right now are using something that was produced using hydrogen fluoride. Okay, so it is one of the major chemicals that's used in semiconductor manufacturing. So if you're using any kind of electronic device that has any kind of chip in it, all right, they use a ton of hydrogen fluoride, and it's one of the issues they need to take care of in terms of making sure their waste is acceptable to release. Because so for example, GlobalFoundries uses 10 million gallons of water a day from the Albany County reservoir. And because they use so much water, they try to recycle 80% of it, okay? But in order to reuse it or in order to release their waste, the amount of HF that gets in there has to be essentially undetectable, okay? It's county regulations because they want a safe water supply. So anyway, that's your trivia about HF. And it's a molecule made of hydrogen and fluorine. And remember that hydrogen has only one valence electron, whereas fluorine has 7 valence electrons. So the hydrogen can, get to the helium electronic structure by sharing one electron, and fluorine can get to the neon electronic structure by, sharing an electron with another atom. So they do that. They form one single covalent bond, okay? And we represent, again, that bond by one single line drawn between the two atomic symbols. Now, there are other valence electrons in the fluorine, okay? 3 pairs of them, as a matter of fact. And they are not participating in bonding, but they are in the valence shell of fluorine, okay? And we call these lone pairs, right? And the lone pairs, okay, which you learned from lab last week, hopefully, is that the lone pairs in a molecule are going to have some impact on the structure of that molecule, okay? And the structures of molecules turn out to be very, very important. So features of molecules that are important for their function. Let me just skip ahead one slide, and then we'll go back to interpreting Lewis structures. So why are we bothering thinking about Lewis structures and drawing Lewis structures? Okay, because they tell us things like how many bonds do we have? What types of bonds are there? Okay, so if we have 2 bonds between 2 atoms, okay, that would be a double bond. So that we call bond order. Is it one connection between the atoms? Is it two? Is it three? And that will tell us something about the physical behavior of the material. It'll tell us how stable it is, okay? The electron pair geometry is going to tell us about shape. And that shape, okay, is going to have a influence, okay, on something called molecular polarity, okay? And so does the molecule act like this neutral thing, or is one end positively charged and one end negatively charged, okay? And so when we get down to it, chemical reactivity and the physical properties of materials, okay, all trace themselves back to the electronic structure of molecules, okay? And so it can be really, again, if we're trying to understand how molecules behave and how chemicals behave, if we're trying to use them for, to do good things, or even if we're trying to use them for doing evil things, we have to understand the elements at their most basic, okay? All right, so interpreting Lewis structures. So before we begin to draw a bunch of them, let's look at a couple and say, well, what do these things tell us, okay? All right, so if we look at this one over here, on the left, okay, we've got, this one is a little more, it's a little larger molecule than we've seen. What on earth is going on with my, sorry. Just realized, got my highlighter set on teeny tiny. All right, so we would call, when we draw a Lewis structure, we'll call something a central atom, right? And so in this case, we have two central atoms here. What is going on with this? There. All right, so we have two central atoms here, okay? And we can look at the connection between those two central atoms. So we see that there are two lines, okay? So that represents 4 electrons, right? So 2 bond pairs is equal to 4 electrons, okay? We call that a double bond, okay? And again, I'm going to introduce terms that you're going to be using later on, but double bonds we call pi bonds, okay? And we would use the symbol pi like you would in mathematics, okay, for that. All right, and then from this Lewis structure, we see that those two central atoms are each attached to 2 hydrogen atoms, okay? The atoms that are on the outside, okay, of a molecule, we call the terminal atom, okay? So the things that are in the middle, we call the central atoms. The things that are in the outside, we call the terminal atoms, okay? So these two down here, okay, are also terminal atoms, okay, because they're on the outside. So they're connected by a single bond, okay? That single bond, okay, is 2 electrons being shared, one from the carbon, one from the hydrogen, okay? And single bonds we call sigma bonds, okay? So this is a sigma bond. And the symbol we use is the lowercase Greek letter sigma. So it kind of looks like the flying O of Oneana, only tiny. All right, so this molecule on the left here, okay, is made up of carbon and hydrogen. Hydrogen forms 1 bond. If we look at carbon, carbon is in group 4A. So to get to 8 valence electrons, it's going to participate in 4 covalent bonds. And so if we counted these, we'd see, this carbon is involved in 1, 2, 3, 4 bonds, okay, as is the other one. And none of these elements in this structure have any pairs of electrons that aren't involved in a bond, so no lone pairs. Okay. Now, if we go and look at the molecule on the right, okay, which is comprised of iodine and chlorine, okay, both of which are halogens. Okay, so they're both in group 7. So they both need to form only one bond, and they can do it with each other. Okay? But in this case, okay, we wind up having 3 lone pairs on each atom. All right, so we've got bonding pairs, we've got sigma bonds, pi bonds, we've got lone pairs, and we have central atoms and terminal atoms. So that's all the terminology that we use, okay, when we're talking about Lewis structures. Okay? All right. All right, so we've got some rules, and the handout that I gave you, if you go through, okay, and you just step-by-step follow these rules when you're dealing with atoms and trying to draw a Lewis structure, right, things should work out for you. Okay, but let's talk about the basic rules. So the first general principle that we follow, okay, and again, this doesn't work for things beyond, this doesn't work consistently for things beyond the third, much beyond the third row. It depends on where you are on the periodic table. Okay, so, but it works really well for molecules that are found in, say, organic chemistry and things like that. Right, so this is the octet rule. Okay, and what it means is that your atoms are going to form bonds so that they can be surrounded by 8 electrons, or if you're hydrogen, it's going to be 2. Okay, because it's uniquely small. All right, so again, when you get 8 electrons in your valence shell, what does that mean? It means you're going to have a p orbital that's completely full and an s orbital that's completely full, right? So you'll have a single s orbital and 3 p orbitals, and they're all going to be full, okay? So they'll be full if the octet rule is satisfied. So when we draw Lewis structures, we count up and, are there 8 electrons around this atom? Are there more? Or are there less? Okay. All right. So if you're going to figure out if a Lewis structure is correct, okay, what you're going to do is you're going to add the number of lone pair electrons and the number of bonding electrons. Now, remember, one bond is 2 electrons, right? So a bond is 2 electrons. One bond equals 2 electrons. So don't forget that when you're counting. All right. So again, your number of valence electrons is related to your group number, right? We said in groups 1 through 4, it's just the group number of the element, okay? And for groups 5 through 7, it's 8 minus the group number. Okay. So this is your halogens have 7. Your chalcogens, that's the group that's oxygen is in, have 6. And then group 5, which doesn't have a name, well, let's just call it nitrogen's group, has 5. Okay? All right. Wait a minute. Never mind. This is number of bonds, not number of valence electrons, number of bonding pairs. Sorry. All right. Number of bonds, your group number of bonds, 8 minus your group number. So rather than remembering these little things, just remember, how do I get to 8? That's what's going to be how many bonds you form, okay? All right. Okay, so we're going to have some exceptions to Lewis structures, okay? the first one we've talked about, it's hydrogen. It's small. It can only accommodate 2 electrons around it. It's only ever going to form 1 bond, and it never has lone pairs. Okay. So the other one is the other exception is boron. Okay. Excuse me. So boron is going to form only 3 bonds. Okay, so that's one of our most notable exceptions. And boron is in group 3. Okay, so let's go up here. So boron is in group 3. So that has 3 valence electrons, right? So to get to 8, you would think it would form 5 bonds, right? But it doesn't. It only forms 3, okay? So you'd expect it to form, 5 bonds. But it only forms 3. So boron is in an interesting position, okay? If you look at your periodic table, so take your periodic table out. What's interesting about boron, considering how it compares to the rest of its group? So what's different between boron and aluminum, gallium, indium, thallium, and yttrium? Yeah? Yeah, boron's a metalloid and the others are all metals. Okay? And what do we know about aluminum? Does aluminum form an ion? From from when we were looking at the common ions, remember aluminum forms a +3 ion, right? So aluminum forms an ion instead of, participating in covalent bonds, but boron is more likely to be found in covalent compounds. So again, it's kind of consistent in that, aluminum would have a charge of +3, and so, boron forms 3 bonds, even though you would expect it to form 5. All right. So when we get to the 3rd row and beyond, okay, or the third period, the 3rd row, you can go beyond the octet rule. Okay, so we'll look at a couple of examples of that. Okay, but if we look at sulfur is in the 3rd row. Okay, sulfur, okay, is in group 6. Okay. So that, by all accounts, sulfur should participate in how many bonds? How do we go from 6 to 8? Yep, we would form 2 bonds. But this is a thing that exists, sulfur hexafluoride, forming 6 bonds. Okay, so this, what this is called it's called expanded valence. So that's one of those examples of where we're exceeding the octet rule. Okay. Now, some stable molecules are also going to be forming bonds with odd numbers of electrons. Okay? And we're going to talk about odd numbers of electrons in the context of talking about things called free radicals. Okay, so you've probably heard of free radicals. If only in cosmetics commercials or nutritional ads and things like that. Antioxidants helping, get rid of free radicals and things like that. So we'll talk about what those are, but they're essentially molecules that have an unpaired electron. And so if you have molecules with odd numbers of electrons, you're going to have an electron that doesn't have a partner, that's not paired. You're going to have a radical. Okay, so call them free radicals. Okay. All right. So how shall we proceed? Okay. Well, we're going to go stepwise, right? We're going to start by counting, okay? So whenever we're trying to solve some type of problem in chemistry, okay, at the end of it, once we have, you know, an idea of how we're going to solve that problem, okay, we have ways of checking if we're right, okay? So starting by knowing how many electrons you're dealing with, okay, is going to help you at the end because you'll have a Lewis structure, and you're going to say, okay, how many electrons are in my Lewis structure? And you compare that to the number that you started with, and you'll know, okay, I've placed all the electrons that I had to place, okay? All right, so you're going to count the valence electrons. So for every element that you're going to be working with, you're going to be looking up its group number and figuring out the valence. So for the example of PF3, okay, phosphorus has 5 valence electrons, okay, and then fluorine, each fluorine has 7, okay? So 3 times 7 is 21, plus 5, that gives us 26 total electrons, okay? So I know in the end I have to have a combination of 26 electrons, whether they're lone pairs or in bonds or whatever. So the next thing I need to do is know what's my central atom, okay? And so we're going to be arranging the atoms. We have to pick a central atom, right? Pick a central atom. And so the way we do this, okay, is we think about electron affinity, okay? So the central atom is going to be the one that has the lowest affinity for electrons, okay? Later on in this chapter, we talk about electronegativity, so it will be the atom with the lowest electronegativity, okay? If we're trying to put it in terms of the periodic table, okay, fluorine is our atom with the highest electronegativity, so we can either use electron affinity trends that we know from the periodic table, or we can look at fluorine, figure out where the element that we're thinking about putting as a central atom compares to where fluorine is. The one that is farthest from fluorine is going to be the central atom, okay? So the other thing is, you know, hydrogen is never a central atom, okay? So we want, so we want farthest from fluorine, and not hydrogen, okay? That's what's going to be your central atom. Yeah?
Is it always going to be farthest from fluorine, or is it only because we're using PKF?
It is always the one that's farthest from fluorine. So let's look at the other sample compound we have here, okay? We got carbon dioxide, okay? So we've got 16 electrons that we're going to have to pair. Let's look at carbon versus oxygen on the periodic table. Which one is farthest from fluorine?
Carbon.
Carbon. And that's the one we put in the center, okay? So this is a general rule, okay? So let's put that down so that So it doesn't matter whether your compound has fluorine or not. The central atom is going to be the one farthest from fluorine on the periodic table. So fluorine is going to be one of those elements where, you know, you're going to hopefully remember a lot of facts about fluorine by the time this course is over, okay? It's the most electronegative. It's got, you know, it has a high electron affinity. It's a halogen. It's got 7 valence electrons. And it is our reference point for comparing elements to see who goes in the middle of a Lewis structure. All right, so the next thing we're going to do is we place the terminal atoms around the central atom, okay? And then we're going to connect everybody by one bond, at least, okay? So here we are with our PF3, and we've added one bond between our central atom and each of the things. And so then remembering that each bond represents 2 electrons, we count up and see how many more do we have to place, okay? So in this case, we've got 3 bonds, right? So 3 bonds is equal to 6 bonding electrons. So we subtract that from the total number we know we had. So we had 26. And so we have 20 electrons that we need, okay, to add. In the case of carbon dioxide, okay, we've got 2 bonds, right? So that's 4 bonding electrons. And so we have 12 electrons left to place. Okay. So the next thing we do is we take all those extra electrons and we put them around the terminal atoms as lone pairs. Okay. So once we have the octet rule satisfied for all of our terminal atoms, if we have any electrons left over, okay, then we add them to the central atom. So if you look at what we've done here, okay, I'm going to zoom in on these guys, okay. We've got, we put our 1 bond in for each, okay, and then I have got 20 electrons to go. So I just go, and if I look at this, okay, if an atom has 1 bond to it, it's going to need 6 more electrons to get to the octet rule. So we would go 1, 2, 3, 4, 5, 6. I do that for all 3 of the fluorines, okay? And then I say, okay, 6 times 3 is 18. I had 20 electrons that I had left to place. That means so I've got 18, oops, let's make this smaller so that we can actually see what I write. So I've got 18 electrons in lone pairs around fluorine. So that means I need to put 2 on the phosphorus, okay? And so that's how I get to this lone pair here. All right, so I have placed all my electrons. I can count up and say, okay, I started with 26 electrons, and so if I've got 18 around the fluorine as lone pairs, 19, 20 for the phosphorus, and I've got 3 bonds, 1, 2, 3, 4, 5, 6. I've got 26 electrons placed. Okay, I'm good. But there's one more thing I need to do, and I just need to do a check and see, have I satisfied the octet rule? Okay, so for the fluorines, okay, I know I have done that, right? Because when I added these lone pairs, I made sure that added up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, when we're counting electrons in a Lewis structure, we're kind of double counting the bonding electrons because they kind of go with 2 atoms. Okay. So when I try to count up on fluorine, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So for this molecule, okay, I have satisfied the octet rule for all of my atoms. Now, let's look at carbon dioxide, okay? All right, so for carbon dioxide, I'm going to follow the same procedure. I've added my 2 bonds, okay? I've got to add 12 more electrons, okay? So I start by adding them to the oxygens, to the terminal atoms, to make sure the terminal atoms get 8, right? So they've got 2 from here, and so I'm going to add 6 as lone pairs. I'm going to do that to both of them, right? Okay, so I've added my 12 electrons. I'm all done, right? No, I'm not, because now I need to check that every atom in my molecule is happy. Every atom has achieved its bonding goals by satisfying the octet rule. Okay, so if we look, my oxygens, yeah, they're good to go. But what about my carbon? How many electrons are around my carbon? It only has 4, right? So, carbon only has 4. So the way that I can kind of resolve this issue, okay, is by taking my lone pairs, okay, and turning them into bonding electrons, okay, by sharing them with the carbon, okay? And so that's what I do. So my lone pair, I'm going to take one lone pair electron here, and I'm going to add an additional bond, okay? So this is, I'm going to make a double bond between the carbon and the oxygen, okay? And so now, when I count things up, okay, those lone pair electrons that became the bond, they're still associated with that oxygen atom. That oxygen atom is still satisfying the octet rule. But now, when I look at my carbon, okay, I've got, if I do that with the oxygen on both sides, okay, what happens is now my carbon has 4 bonds. Each bond is 2 electrons, so that's 8 electrons around it. Okay? So the very last step that we do when we're drawing Lewis structures, okay, for molecules that only have one Lewis structure, okay, is going to be, you know, adding double or triple bonds, whatever I need to get to where I'm going, okay, to satisfy that octet rule. So, whoop. All right, so that's my basic procedure. This guy should be our little, imagine he's our little chameleon. This is a recycled slide from when a bumblebee was the team mascot, or the class mascot, so. All right, so we got one other thing going on, and the other thing that's going on is that just ignore that. Is that we can have the equivalent Lewis structures. So, oops. We'll talk about calculating the formal charge later, but we're gonna do some examples. So we did this on a previous slide. That was the one that we did on the slide with the rules, right? So, see the previous slide. I'm just gonna delete the slides that I duplicated. All right. All right. So let's do CO3 2-, okay? All right, so first we're going to count our valence electrons, right? So we've got carbon. So carbon has how many valence electrons? Carbon is in group 4. Okay, so carbon has 4 valence electrons. How many carbons are in our compound? 1, right? So this is 4 electrons times 1 carbon atom. So we've got 4 electrons from the carbon. Oops. Oxygen. Okay, we've got 3 oxygen atoms. Okay, and oxygen is in group 6. So oxygen is the oxygen atoms, those 3 oxygen atoms, are going to contribute 18 electrons. Have I accounted for all of my electrons? Well, I've counted the number of electrons in a neutral carbon and a neutral oxygen, right? Ben?
Has a -2 charge, so it has 2 more electrons.
Right, so we've got 2 extra electrons. All right, so this is a total of 22 electrons plus our 2 extra electrons. So I've got 24 electrons. All right. So who's going to be our central atom, carbon or oxygen? It's going to be carbon, further from, so we'll put our carbon here, right? And we'll put our 3 oxygens just arranged around it. Okay. All right, so we did that. Now we're going to add our single bonds, right? So we'll add our single bonds in black. 1, 2, 3. Okay. All right, so how many electrons do we have left after adding 3 bonds? So we had 24 to start with. And we've done 3 bonds. Okay, so that's 3 bonds times 2 electrons apiece. So that's 6. So that means we've got 18 electrons remaining to place. Okay? All right, so I'm going to place those remaining electrons. Okay, we're going to do that in red. And so we'll do them around the oxygens. Okay? So if we've got 1, 2, 3, 4, 5, 6, that makes him octet rule satisfied. All right, what is 3 times 6? 18, right? So all the oxygens get 3 lone pairs. Aha. Our last thing we need to do is we need to check the octet rule, okay? Oxygens are okay. How about the carbon? Nope. Our carbon has how many electrons around it? It's only got 6. All right, so how do we deal with this situation?
Put a double bond on there for one of the oxygen.
Yep, we're going to put a double bond on. Okay, so I'm going to take this one and move it there. Okay, so we need 1 double bond. So my structure, okay, winds up looking something like this, where we've got only 2 lone pairs on one of the oxygens, okay? Now, we also need to indicate, okay, that there are extra electrons in this species. So, one of the ways we can do that is we can put brackets around it. Oops. And we can put the charge there, okay? Or sometimes you put the charge, on next to the central atom, okay?
Trigonal planar array.
What's that?
Trigonal planar array.
So for this one, yes. So, all right. So one of the things when you're placing the double bonds, okay, an important rule of thumb to remember, okay, is only a few atoms can form double bonds, a few elements. So they would be carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay. So carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay, so they kind of line up right in a row with the phosphorus and sulfur kind of right underneath the nitrogen and phosphorus. So if we're looking at the periodic table, which I should have right here, let me make this a little wider. So, oops. These guys right here can form double bonds. All right. Yeah.
Is that double bonds or more, or just specifically double bonds?
Actually, it's multiple bonds, actually. So, yeah, double or triple, depending on the situation. Yep. Yep. Yeah, I should correct that on this slide. Let me do that. We're going to change this. It's not going to be double, it's going to be multiple. So that's double or triple. Okay. All right, so the last thing we're going to talk about this week is exceptions. Now that we've gone over a whole bunch of rules, we're going to talk about ones that don't follow this rule. Okay, so there are three general exceptions. Okay, so there are electron deficient compounds. So they have they'll be have an element that has what we call an incomplete octet. Okay, then we have free radicals. Okay, so they have at least one unpaired electron. Okay, so this is things like molecules with an odd number of electrons, right? Oops. There we go. All right, so those things are going to come from when you're in things like group 5 and group 7, right? Those are odd numbers of electrons. So in group 5A and 7A, if you have an odd number of elements from group atoms from group 5A and 7A in your molecule, you're going to have an odd number of electrons. Okay, and then the third one, okay, is these are going to be atoms that can have an expanded valence. So some elements can contain more than 8 electrons in their Lewis structure. Okay. So these ones are going to be p-block elements equal to phosphorus and beyond. Okay, so from the third row down. Okay, so what that means in period 3, phosphorus, sulfur, and chlorine can have a expanded octet, and then anything in row 4 that's in the p block down. Okay. Because if we go back to just thinking about orbital filling, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. I'm just going to draw those, okay? So if we think about the order that things are going to fill in, okay? When we get, so we go this way and there, right? When we get beyond the third row, okay? When you wind up having some d orbitals, okay, that are going to get filled before your p orbitals, right? And so you're going to have spaces available to you, beyond that S and P that give you nice 8 electrons when they're both filled, okay? So these larger elements are going to have these other orbitals that will have a tendency to be able to have electrons in them, okay? All right, so let's talk about IF3, okay? So IF3, okay, is going to be an example of our kind of expanded valence. We're going to be able to go beyond the octet rule for this molecule, okay? Iodine, way beyond the third row, okay? It's in the p block, okay? That's our element that's going to be able to have more electrons on it, okay? All right, so let's count our valence electrons from iodine, okay? It's in group 7 as well as the fluorine, okay? So both of them have 7 electrons. We've got 1 iodine atom, so that's 7. And then we've got 3 fluorines, so that's 21. So we have a total of 28 electrons, okay? All right. Who's going to be our central atom here?
Not fluorine.
It's not fluorine, that's right. It's going to be the iodine, right? So the iodine is going to be in the center, and we're going to have the 3 fluorines around it, okay? So the next thing we're going to do is we're going to add our single bonds, okay? So I'll put those in pink this time. 1, 2, 3. Okay, so we did that. All right, so that took care of 6 electrons, but we have 22 electrons left, right, to place. So here we go. Let's place those remaining electrons. We'll put those in green, okay? So we've got 1, 2, 3, 4, 5, 6. So if we put 6 around each of the fluorines, they will satisfy the octet rule because the bond gives them the extra 2 electrons that gets them to 8. All right, so I have 6 times 3, okay, so the lone pairs on the fluorines take up 18 electrons, okay, but I have, how many more do I have? I've got 4 left to place. And so where do they go? They're going to go where they can go. They're going to go on the element that's beyond the 3rd row. That is, again, not phosphorus or sulfur, right, or chlorine. So they're going to go on the iodine because it can take them, okay? So it's beyond the 3rd row. So we're going to put those 4 electrons on the iodine, and I'm just going to put them kind of on either side of it. Oops. Come on, there we go. Just move that a little bit. All right, so now when I check my expanded, or when I check my octet rule, okay, fluorines are fine, okay, but the iodine, how many electrons does the iodine have around it? It's got 3 bonding pairs, right? That's 6. And then it's got 4 more electrons, so that's got 10 electrons around it. And that's, again, it's okay because iodine can accommodate extra electrons, okay? First of all, iodine is way down the periodic table, so it's pretty large, okay? So it's, and it's going to have empty d orbitals, okay? Because if we look, okay, so iodine is, element number 53, but it's in the 5th row of the periodic table. So that means it's going to wind up having 5 electrons in the 5 p orbitals, right? But again, there are going to be some 6s orbitals that are going to fill before the 4f orbitals, and so it's got these extra orbitals that are around it that can accommodate those electrons, okay? All right, so again, it's beyond the 3rd row. All right, so we're going to stop there, and what we're going to do next class is we'll go through examples for our other 2 exceptions, and then we're going to talk about resonance and charge distribution in molecules, okay? Have a great weekend, everyone. I will get both